Okay, shut up now. This is my time to shine. I've been up all night preparing this lecture. Who remembers the units for stress? The SI units for stress? Pascal, yeah. And who remembers the units for strain? It doesn't matter whether it's SI or... yeah, kind of a trick question. But it's important, you know. SI units for stress...
A meter over a meter.
Yes.
A meter per meter.
SI units for stress are pascals. A lot of times stuff will be done in megapascals because the stresses are going to be big. And the units for strain it's unitless. We talked about normal strains last time, and we started talking about, I guess we sort of talked about what the shear strains are too, but I'm going to illustrate it a little more this time. Okay, so the shear strains have to do with changes in angle. And so if this is your undeformed piece and it turns into something like that, and our coordinate system is this. So I'm always going to assume that our starting piece is rectangular, so those angles are starting out at 90 degrees. Then this is the positive x face. This is the positive y face. You're with me on naming those faces. Think of the alien living inside, and which face the axis points out of. Okay, so the angle we care about then is the angle after deformation between the positive x and y faces. Okay, so we don't care about this one, because that's the negative x and positive y face. Okay, we don't care about this one because it's negative x and negative y. Okay, we only care about the angle between the positive and the positive. And so this is the angle that I'm going to call theta x, y. And so this thing, theta AB, is after deformation, you know, it's the deformed angle come on. Okay, so this is the theta x, y. So if we have this thing we're calling theta AB, that's the deformed angle between the positive A and the positive B faces. These angles have to be in radians. And so what we're going to call the shear strain XY is pi over 2 minus theta XY. The shear strain gamma XZ is pi over 2 minus theta XZ. Gamma YZ is pi over 2. Oh no. Oh no. It's going to crash again. God dang it. I'm getting all this good practice writing this stuff. I feel bad for you guys for having this already written on your paper. And again, this is unitless because these are radians. Okay, so let's see an example. What if that starting piece wasn't rectangular, by the way? What if this started out as like sort of a trapezoid kind of thing? I guess it would have to be a parallelogram of some kind. But then this, you just have this starting angle wouldn't be pi over 2. It would be whatever the starting angle was. Okay, all right, so let's say we start with a piece that's rectangular, so all these are 90 degrees. And it deforms into something like this, where this angle is 1.43 radians. Okay, but we're also going to assume that crash. Okay, I wonder if I'm... Okay, hold on. I have 339 gigabytes free. That seems like that should be enough. All right, good luck to us all. Okay, so, but we're going to say this isn't in the XY plane. We're going to say this is in the, what do I have here? X is this way, Z is this way. Okay, so everything's like topsy-turvy. And we want to calculate gamma XZ. Okay, so the first thing you have to do is identify the two positive faces. With this crazy coordinate system, this is the positive Z face, and this is the positive X face. So the angle we really want is this. Okay. It's a parallelogram, so those have to add up to pi. And so so this is the angle that we want, XZ. And so XZ is equal to 3.14 minus 1.43 And so that's like 1.71. And so gamma xz is pi over 2 minus 1.71. And that is negative 0.28. Well, remember I said that if an angle becomes more acute, the shear strain will be positive, and if it becomes more obtuse, it'll be negative. So this makes sense. Right? And then what about the size? Is that a reasonable size for the materials we're dealing with? No, 0.28 is way, way bigger than 10 to the minus 4. So this is not realistic, although, we did the math right and stuff. It's just you wouldn't ever see a strain like this in a piece of steel without doing permanent damage to it, So this is not realistic. Okay, so now how do you represent the strain? We talked about the stress tensor and the Voigt stress. With strain, there is such a thing as a strain tensor, but not in this class, there isn't. The way we're doing it, it's not a tensor. So the only way we're going to represent strain is the Voigt strain. And the Voigt strain I'm going to represent it epsilon sub v, and it's just in the order you would think, the exact same order as the Voigt stress. It's the 3 normal strains in order, and then the 3 shear strains in the most nonsensical order possible. YZ, XZ, XY. Okay? So now we're going to the constitutive relationship. This is such an important day, actually. Constitutive relationship. So I said that we're talking about Hookean materials that mean the stress and strain is related by a matrix of constants. Okay? So this is a Hookean material. And that means we're going to use the 3D version, a 3D version of Hooke's law. And here's the way we're going to do it. The Voigt strain is equal to a matrix times the Voigt stress. This is the one we're going to see the most often. It also says this. You could write it the other way, that the Voigt stress is equal to a matrix E times epsilon Voigt. If you do it this way, this matrix C is the 6 by 6 compliance matrix, it's called. If you do it this way, this E is the inverse of the compliance matrix. I'll talk about that soon. And this is called the stiffness matrix. It's also 6 by 6. And think about a chunk of steel. And think about, okay, so you have a rectangular piece of steel and you just whack it into your head. Just imagine doing that. Do you think after you did that, you would think to yourself, wow, that is really compliant? Okay, so you would not think that. These values are really small. It has very low compliance. These values are going to be like on the order of like 10 to the 10th or 10 to the minus 10th, something like that. On the other hand, after you whacked it into your head, would you think, that was pretty stiff? That's more likely that you would think that, and so these are going to be really large values. Okay, so let's talk about this compliance matrix. I'm not really going to talk about the stiffness matrix because you can just make your calculator take the inverse of it, you know. So I'm just going to talk about the compliance, and if you ever need the stiffness, just take the inverse, okay? And I'll tell you, we'll talk about that a little later on, but what about the compliance matrix? Okay, just because there's a 6 by 6, so 36 element matrix that relates these two things, doesn't mean that it's possible to come up with the 36 values that define it, right? It's a 6 by 6 matrix. So that means 36 values. Imagine this nightmare case where you had all these very tricky measurements to do on a lump of steel or whatever to figure out how to fill in this matrix for the steel you're using. Even though mathematically it's a thing, it might not be practical to do. Well, it turns out, so that could be, let's say that could have been really hard to measure values for. But for the materials that we're considering in this class, and those are materials that behave the same in every direction. If you have a lump of steel, you don't have, and you try to stretch it one way, it won't be harder to stretch this way than this way. There are some materials that are that way. Any materials that have a noticeable grain will be stronger one way than the other way. Wood will be stronger one way than another. Actually, bone will be a little stronger one way than the other. Stuff coming out of a 3D printer often is stronger one way than the other because it has a grain from the way the stuff is being laid down.
Actually, steel does have a grain.
Well,
It's not like...
if you can make steel, you can make it to have a grain, but for the most part, like just steel that you've, the crystals are going every direction. And so it just averages out to behaving.
It was forged or there's forged and there's cast, yeah, sorry.
Uh-huh.
But like the forged, like all made materials for airplanes,
Uh-huh.
and especially aluminum, the grain has to be away.
Huh.
Because it does. I mean,
Yeah.
probably in this class they're gonna.
Yeah.
But like for the most part, when you have a forged part, especially forged
Mhm.
steel or aluminum, it has a grain. You cut it, and you can actually see it.
I guess I can picture that with aluminum.
And then if a lot of times it'll be rolled.
Yeah.
Oh
yeah.
You actually see the grain
Huh.
because it has like the roll.
Yeah.
It's kind of weird, but
okay.
Probably for this class.
Okay. Well, let me change what I said. Well, I'll just keep it like this. The materials we're considering in this class.
Yeah.
And that's interesting.
In high performance engines, you need like forged pistons and forged crankshafts.
Uh-huh.
So,
huh.
Because they're lighter as well.
Yeah.
But you need
huh. That's really interesting. I did not know that. The materials we're considering are what's called isotropic. That means they have the same behavior in every direction. The 36 values of this matrix are completely dependent on two parameters, and those two parameters are really easy to measure for a material. It's kind of amazing, you know? So those 36 values are completely defined by two material parameters. That are easy to measure. Okay, those two parameters are capital E, that's called Young's modulus, or the modulus of elasticity. Or the stiffness. And the second one, for metals, let me give you sort of a ballpark range for this. The range is somewhere around 100 to 200 gigapascals. So 1 times 10 to the 9th pascals. And then the second parameter is the Greek letter nu. Looks like sort of like a V, cursive V. This is called Poisson's ratio. And for metals, this is usually around 0.3 somewhere. To find these values for the material that you want to do simulations for, you get the stiffness and the Poisson's ratio from a tensile test. And the way a tensile test works is you make some uniform piece of material like this, usually like a rectangular strip, and you put it between two very strong clamps. Obviously, the forces we're going to be talking about with this are pretty huge. So this is the material sample. And you apply forces like this. So basically you just have to stretch that material a little bit. We'll use a coordinate system for this always that has the x-axis along the long axis of the material. And y and z then are perpendicular to that. Okay, so what you do is MTS, it's a huge Minnesota company that does testing. They started out, I think, making these tensile testing machines. I mean, they have to be very strong and they have to be very precise. And you apply however many thousands of newtons of tensile load, and you very carefully measure the change in length of this material along each of those three axes. Okay.
So they just test all these materials and send out information?
The company MTS?
Yeah.
They make machines. So like at the University of Minnesota, they had a machine for doing this. And they also do a lot of like one-off testing for like vehicle manufacturers and stuff that, you know, the company says like, we're going to send you this vehicle to find out like what, you know, it can withstand for this kind of thing. And they just do a lot of like figuring out how to test that stuff. I think that's a bigger part of what they do now than this, but this was how they started, I believe. Okay, so to measure the stiffness, so first, the normal stress in the x direction is that force F divided by the cross-sectional area. So this F is the tension force, the tensile force. A is the cross-sectional area. The normal strain is the deformed length minus the starting length divided by the starting length. And then once you've measured those two things, the stiffness is just the stress divided by the strain. Okay, well, this stress is going to be in the millions, and you're dividing by something that's maybe a millionth. So you're going to get this huge, huge number. And since the denominator is unitless, the units for the stiffness are going to be pascals again. So that's to measure the stiffness. Then to measure the Poisson's ratio, you need a third measurement. You need to measure the strain in one of those two off-axis directions. So you need either a Y strain or a Z strain. I'll call it Y. So this is equal to the deformed length minus the starting length in that direction divided by L sub 0. You could also use the same idea to calculate the Z normal strain. And then the Poisson's ratio is negative EYY over EXX, which is going to give you the same value as negative EZZ over EXX. There's a range of possible values here. And that's 0 to 0.5.
Why the negative sign?
Because these are always going to be in the opposite direction from each other, so it's just to get a negative, just to get a positive value for Poisson's ratio. Because what this is measuring is, like, if you push on something, it bulges out, okay? And if you pull on something, it sucks in. Okay, we're pulling on this thing, so it's going to suck in. So we're going to have a positive value of strain in the loading axis direction and a negative value of strain in the two off-axis directions. Okay. To get this value, you need to have, this would be if volume is always going to be conserved. So if you measured the Poisson's ratio of, like, if you filled a rubber membrane or something with water, and water is incompressible essentially, and you did this test, you would get 0.5 for it because it can't be compressed. Okay. Cork has, most things have some positive Poisson's ratio. Cork has essentially a Poisson's ratio of 0, which explains why historically cork has always been used to seal bottles. Because if you wanted to seal a glass bottle with a piece of steel or something, and you fit it and put it on top and whacked it with a mallet, that compression in the loading axis would make it bulge out on the sides, which would break the glass. Cork, though, you can smack down on it and it doesn't bulge out, and so that's its, strength for that application. Okay, so now this is the punchline of the whole class. Now that we have those two values, whatever you're trying to measure, assuming it's isotropic, the compliance matrix is this. So here's that 36 element compliance matrix. I think I actually wrote this once before already, but so the first row is 1 over E, negative nu over E, negative nu over E. It doesn't hurt to write it again, unless you have a sore hand. The second row, so remember that 1 over E just keeps bopping along the row. So now for the second row, we have negative nu over E, 1 over E, negative nu over E, 0, 0, 0.
Why did we make the new positive on the last step and take it negative?
I don't have the answer to that. I just want to remind you again that I didn't make any of these rules. And then the third one, negative nu over E, negative nu over E. I guess probably the answer is like people, it probably was a thing long before people put it into like a full matrix form, you know? So they used it for, that's probably why. But negative nu over E, negative nu over E, 1 over E, 0, 0, 0. And now for rows 4, 5, and 6, we have zeros for the first three elements. And the thing that moves along one at a time is 2 times the quantity 1 plus nu over E. Okay. So for this entire class, everything we do in this class, this matrix defines the relationship between the Voigt stress and the Voigt strain. So in every case, if you know the stress, the Voigt stress, multiply it by this matrix, and it'll tell you what the strain is for that material at that point. That's pretty amazing. Like in a way, we're sort of done with the relationship between stress and strain now, you know? Question?
Didn't you say there was a matrix that was the inverse?
Yes. Yes. So
isn't this matrix symmetrical though? Across the.
It is symmetric, yep. But a symmetric matrix, yeah, there's nothing weird about the inverse of a symmetric matrix. So, I mean, yeah, you can take the inverse. And what are I don't remember what the values look like. I don't think I have them written down here, but you can see that all of these values are tiny because you have pretty small numbers divided by something gigantic that's like 10 to the 10th or whatever. If you take the inverse of it, all of the non-zero elements are huge. So this is the compliance steel. Yeah.
For some reason, I was thinking that was the thing where xz turns into zx.
Oh, okay. That's the transpose.
Transpose. Okay.
Yes.
That's right.
Yes. Right. There are certain types of matrices where the inverse is the transpose, but it's not always true. Rotation matrices, for example, the transpose is the inverse, which makes it really easy to take the inverse. But it's pretty easy anyways, unless you have a gigantic matrix. Okay, here's the last thing I want to say today. Yeah.
What do the placement of the values mean? Like, you know, for example, when you're doing the stress tensor, right? And that's like a reason for where there are.
Yeah.
So what does that represent here?
Here, I mean, it's just telling you what, so you're always multiplying this times the Voigt stress. So what this is saying is to calculate the XX Voigt strain, okay, you're taking 1 over E times the XX Voigt stress minus nu over E times the YY stress minus nu over E times the ZZ normal stress. So to calculate the strain at this point, you have to include all of the normal stresses. Same with this and same with this. So to calculate the normal strains, to calculate any individual normal strain, you need all three normal stresses. but the shear stresses don't come into it. Then to calculate the shear strains, the only thing that matters is the corresponding shear stress. Okay. And that's actually, there's at least one question where I'm going to ask you to just sort of think about those relationships, like what measurements would you have to know? What stress, sometimes you don't want to calculate every single stress value in the Voigt stress. If all you want to calculate is the XX strain, how many stress values would you need? And this tells you that story. Okay, so now, this is the relationship between stress and strain under certain conditions. Here are the conditions that we're always going to be considering in this class. So these are the 4 big assumptions that we're going to make. In this class. The first one is that the deformations are small. Once the deformations get out of a certain range, you don't have this linear Hookean relationship anymore between stress and strain. And the deformations, it's right around the point. So we basically are considering deformations right up until about the point where a material starts to be deformed permanently. Okay, so if you stretch a steel bar a tiny amount and let go of it, it returns back to its original length. If you stretch it a little too far, it'll have a permanent stretch. And that's about the cutoff that we're considering in this class, okay? So we're considering everything to be elastic. If you remove the load, it returns to its original shape. So small deformations, that means, like I've said before, strain values less than about 10 to the minus 4. Second, we're assuming linear elasticity. That's the same thing as saying we're assuming it's a Hookean material. And we just came up with that linear relationship. The Voigt strain is the compliance matrix times the Voigt stress.
So meaning isentropic, is that what the linear?
The isotropic thing is why we can simplify those 36 values down to only depending on 2 constants. But even if it wasn't isotropic, but it is, you could have it be linear elastic. You just might have a much more complicated matrix. Mm-hmm. But you'd still have that 36 value constant matrix. The third one is homogeneous. Homogeneous means that the material is the same at any 2 points. Okay, so you don't have pockets of this and pockets of this in it. It's all mixed. Okay. So the same material properties at every location. So like a chocolate chip cookie is not homogeneous, but a sugar cookie is homogeneous. Okay. And like when they homogenize milk, you get the milk and it has like dead animals in it and blood and pus and stuff. And then they just mix it all up and then it's consistent.
They would change.
Would like a steel alloy be homogeneous, or would that?
Yes, correct, yes. And then the last thing is isotropic, which means that sometimes it's a little hard to keep these two straight. Homogeneous is comparing 2 points. Isotropic is saying a single point is the same no matter what direction you look in. Okay, so isotropic means same material properties in every direction. I guarantee I'm going to ask you about these 4 things on quizzes, more than one quiz too. So keep those in mind, you know. Anybody have any questions? That is a great day of class. Like, there is no other day where we're going to cover as much significant material.
It's all downhill from there.
Yeah, that's one way I don't like to think of it that way, but yes, you could think of it that way.
So, is there a way to write a program to just input in the compliance meters? Like,
Yes, for sure there is.
just set it up.
Okay.
Just set
Yeah, like
hey,
if you-
alpha
if you
E
give
and
two
alpha B is
values,
this, and then
you
you just
just
run the
make-
program.